Hi everyone, I'm Bo Xun Wu, and I'm going to present our paper, Data and Camera Fusion for Vacant Parking Space Detection. The authors are Bo Xun Wu, Jiazhen Lin, Xiankai Guo, Po Yuchen, Junying Guo from National Yangming Jiaotong University and MediaTek. Here is an outline of our presentation. First, we will briefly talk about the motivation of doing vacant parking space detection with camera and radar fusion and an example scenario. Then we will introduce our proposed system with breaking down to a few parts. And we will show the setting on the car and demo video to show how well our proposed system can achieve and the whole experiment result. At the end, we will give a quick summary. A typical computer vision face approach detects the parking slots folder according to the frame line on the ground first, and then check whether it is occupied. However, some of the car parts do not show the slots for users, like in this picture. And we want to build a system that can handle this scenario, even in different light conditions and weather. The camera can give a precise location of the vacant space. The radar can work well under dark conditions, and also a stable method to confirm the result. So using these two sensor fusion may well complete this task. And here is our parking lot detection system flow. We process the radar and camera information separately and then combine together with a fusion algorithm. First, we focus on the camera part. The image captured from the camera will go through a deep learning-based insert segmentation (ULEC), and which is a lightweight model that can run on each device in real time. Then the output will transform to bird view and then do our space estimation algorithm. And here is the detailed process with an example image. We have to do the homography matrix for bird view transform after we install the camera on the car. You just need to do once. We will take the 4 points near to the two straight lines, one at the start and one at the end. Assume that they are on the horizontal plane. We can find the perspective transformation with an existing algorithm. And like the right picture is an example after doing the bird view transform. After we do instant segmentation, we collect the front car nearest to the camera and combine the output mask into the one binary map. Then do the bird view transform and we can get the mask for space estimation algorithm. And before doing next post-process, we set a blind spot region shown as the right lines. This can avoid false alarm lag caused by the large distortion outside this region after bird view. And we can project the binary map to x-axis, find the edge of the cars shown as the blue lines. Use the center of the edge and plot a rectangle with our car width, and it would be the expected parking location. And when we are calculating the accuracy of our system, we use the estimated car space, the distance of the two blue lines, and compare with the real space width that we measured to get the error. For visualization, we will transform the green bounding box back to draw on the ground. And we can see that the detection result of camera is quite accurate. And Here comes to the radar part. The radar sensor will give several object points called radar point counts that contain the distance. And we extract the closest object distance for each frame. Over the time, we can plot a distance versus time distribution diagram. And this information will be used for radar space estimation algorithm. And here shows a distance versus time distribution diagram. The x-axis is the number of data radar got, and the y-axis is the distance with the unit meter. And you can imagine as our car drives through from left to right, and we will get a nearest object distance from radar with a specific frequency. Then when the radar is about 7 meters, there might be a space for parking. But if the distance is only about 2 meters, there might be a car parked by. And we can use this information combined with the car velocity to calculate the empty space width and depth. And we can get car velocity from GPS or CAN multiplied by the execution time interval, and we can obtain the distance the car drops. And if the radar object distance larger than 4 meters, it may be a vacant. So we can start to accumulate the vacant space width. And if the accumulated width passes the threshold we set, like 2.4 meters, we will report it as a vacant parking space. With the camera estimation result and radar estimation result, we can use a fusion decision rule to get the final result. We have more confidence on radar decision that only when radar report as vacant, we will determine it as a vacant parking space, because that radar can be workable under most different illumination and weathers. And the camera advantage is that it is high precision of estimating the exact parking location. So after radar said there is a vacant slot, we will first use camera result. If the camera result is not available, we will use the radar estimation result. And we'll briefly introduce our experiment setting. We'll install a radar at a lower place and a camera at a higher place to achieve a better quality. And we use a Logitech webcam with a resolution 640 by 360 and frame rate 30 Hz. And the radar we use is a MediaTek 1T1R FMCW radar, and the max detect range is 20 meters, and that is enough for a vacant parking space detection. Here is a demo to show how our proposed system works. When our car drives past by the parking spot, the system will continuously detecting the vacant space. When a proper location is valid, it will plot it as a screenshot and report the location. And you can see it works properly on different illumination and weather. And the camera detection was bad at night, so we will adopt the radar estimation. And here we collect some screenshots from previous video, and we can find that The radar estimations are valid under all conditions, but not quite precise. And the camera estimation is precise, but not workable at night. So our fusion result will adopt the radar estimation at night and the camera estimation for other conditions. We collect several times of estimating result compared to the actual width, the ground truth of the vacant space. We can see that the radar estimation error rate is only about 5% under different conditions. And for the camera estimation, it's far more precise than the radar, that the error rate is even under 1%, that the actual error of the width is less than 10 centimeters. To summarize, the camera estimation precision is better than radar. However, for dark scenes like night or underground parking lot, only radar can work well as usual. Also, if there is something that the camera model don't know, it may see it as a ground. For example, a dog or some obstacle like a trash or something. So we must use data to verify whether it is a vacant space. So using camera and data fusion, we may have all the advantages and the best location precision. Okay, thank you for your attention.